Observe how a standard, continuous block of material transmits an incoming acoustic wave. The mechanical energy passes through the medium almost effortlessly. But if we replace that solid block with a highly structured one-dimensional lattice, that exact same wave violently scatters and decays. We are looking at a mechanical metamaterial. This is an artificial structure engineered so that its bulk mechanical properties are determined entirely by its internal geometry, rather than the chemical composition of the material it is printed from. The defining principle here is sub-wavelength periodicity. By arranging the internal architecture of a lattice at a scale significantly smaller than the wavelength of the incoming vibration, we can override the macro-scale physics of the object. This structural manipulation allows engineers to force a material to exhibit extreme properties that violate our everyday intuition, like achieving a negative effective mass or a negative structural stiffness. To understand how these structures operate, we have to bypass material chemistry altogether. We analyze them purely through the lens of classical mechanics, deriving their behavior using coupled differential equations. Designing a metamaterial requires an inversion of traditional engineering logic. The geometry of the architecture commands the physics, overriding the base material entirely. This map outlines the academic progression of the mechanical metamaterials discipline. We start right here, calculating wave mechanics in one-dimensional arrays. Once that baseline is established, we layer in real-world energy dissipation, studying how viscous damping and active feedback controls modify the wave attenuation. From there, the math scales up. We apply dynamic stiffness matrices to translate these discrete properties into continuous beams and two-dimensional grids. Finally, we reach the edge of current research, bombarding these structures with high-amplitude waves to trigger chaotic, nonlinear snap-through behaviors and topological boundary states. For this analysis, we are zooming in exclusively on that very first node. We will derive the exact mathematics behind the two foundational phenomena that allow a lattice to stop a wave: Bragg scattering and local resonance. If you want to understand complex continuous systems or chaotic topologies, you have to master the linear one-dimensional arrays first. The math builds outward from here. This animation shows a continuous mechanical wave traveling across a 2D plane. The wave is governed by this standard function, where omega represents the angular frequency of the vibration and k represents the wave number, which tells us the physical wavelength. Observe what happens when this wave travels through a periodic lattice. We place physical scatterers at specific repeating intervals, labeled delta x. At every single interval, a portion of the wave's energy physically reflects backward. The critical mathematical condition for Bragg scattering occurs when the distance between these scatterers is exactly half the incoming wavelength. When k times delta x equals pi, every single reflected wave aligns perfectly 180 degrees out of phase with the incoming wave, causing total destructive interference. This interference creates what engineers call a stop band or a band gap. The vibration is physically blocked from propagating any deeper into the material. But Bragg scattering carries a severe geometric limitation. Because the scatterer distance must equal half the wavelength, stopping a low-frequency wave, which has a very long wavelength, requires building a massive, thick lattice. Bragg scattering is highly effective for high-frequency isolation, but it cannot bend the rules of geometry. By definition, it cannot provide true sub-wavelength wave control. This diagram illustrates the standard lumped parameter model used to evaluate periodic structures mathematically. It is a simple monoatomic chain of repeating masses connected by springs. We define the movement of a single mass in this chain using classical Newtonian mechanics. The equation of motion simply balances the inertia of the mass against the opposing forces of the two springs attached to it. To solve for an infinite chain, we apply Bloch's theorem. We assume the system is undergoing steady harmonic motion, which allows us to replace the time derivatives and convert the calculus into a solvable algebraic equation, isolating nu, the dimensionless wave number. Solving for the wave number gives us the dispersion relation. As we calculate this across different frequencies, we eventually hit a cutoff point where the math forces the wave number to become a complex number. A complex wave number defines exactly how the lattice interacts with the wave. The real part of the number dictates the phase shift across the cell, but the imaginary part dictates how fast the wave's amplitude decays exponentially across space. This discrete algebraic baseline proves the core mechanic. Any standard periodic structure inherently acts as a low-pass filter, completely attenuating frequencies above its specific cutoff limit. To solve the low-frequency size constraints of Bragg scattering, we change the unit cell. This is a locally resonant metamaterial, which embeds a completely separate secondary spring mass system directly inside the primary outer shell. We now have 2 degrees of freedom per cell. We have the mass and displacement of the primary outer shell, m1, and we have the internal resonator, possessing its own mass, m2, and internal spring stiffness, k2. The math expands into a system of coupled differential equations. The outer mass is still reacting to the macroscopic lattice springs, but it is now subjected to a new internal force exerted by the movement of the resonator trapped inside it. We again assume steady-state harmonic wave propagation to drop the time derivatives, converting these coupled equations of motion into the frequency domain. The algebraic strategy is straightforward. We solve the internal masses equation to find its displacement, and then substitute that result directly back into the equation for the outer mass. By mathematically collapsing the internal degree of freedom into the primary equation, we completely decouple the wave attenuation behavior from the physical dimensions of the lattice. Once we make that substitution, the internal mass dynamics modify the primary inertia term. This bracket is the effective mass of the metamaterial cell. Look strictly at the denominator of the internal mass fraction, K2 minus omega squared times m2. As the frequency of the incoming external wave approaches the exact natural frequency of the internal resonator, this denominator shrinks toward 0. Consequently, the effective mass of the entire unit cell mathematically spikes to infinity. The critical behavior happens immediately above that resonant frequency. The value of the denominator flips to a negative value, driving the entire effective mass curve below the 0 axis. In physical reality, an effective negative mass means the internal resonator is now moving perfectly out of phase with the outer shell. When the wave pushes the shell right, the internal mass violently snaps to the left. This severe out-of-phase movement generates an internal, localized negative momentum. The unit cell is generating its own inertial force that pushes directly back against the incoming wave. We have not created anti-gravity. We have manipulated internal kinematics to yield an effective negative mass that stops wave propagation perfectly in its tracks. This is a dispersion diagram, the standard tool engineers use to map these dynamics. Panel A plots the wave frequencies against the wave number for our mass and mass structure. The stark horizontal white space separating the first and second propagation branches is our local resonance bandgap. Within this specific frequency range, no mechanical wave can survive. Inside this exact gap, our previous equations yield a purely imaginary wave number, proving that the wave will suffer aggressive exponential spatial attenuation. Panel B shows the plot for group velocity. This tracks the actual speed at which physical mechanical energy transports through the lattice, derived directly from the slope of the dispersion curve. Look at the exact boundaries of the bandgap. The curve drops until it perfectly touches the 0 axis. When group velocity hits 0, the transport of mechanical energy halts entirely. The math proves that the resonant metamaterial acts as an impermeable physical barrier to the specified frequency. We now have 2 proven mechanisms for wave attenuation. Bragg scattering relies on macroscopic spatial dimensions to cause destructive interference, while local resonance relies on sub-wavelength internal kinematics to generate opposing momentum. Keep in mind that the mathematics we derive today assumed a perfectly linear, idealized, and undamped system. In applied engineering, these physical unit cells possess intrinsic viscous damping. Adding damping into the coupled equations heavily modifies the imaginary component of the wave number, accelerating the rate of energy dissipation. Furthermore, if you subject these structures to high-amplitude shock waves, the linear springs deform. They begin exhibiting nonlinear snap-through behaviors, transforming the lattice into a chain of chaotic Duffing oscillators. Calculating those dynamics requires immense computational power, but understanding this baseline of 1D linear wave mechanics is the strict prerequisite. You must understand how to derive the band gap before you can build the active feedback controls and topological waveguides of the future.